Okay, so we've done the logistic regression parameter update. Now I guess the most natural thing to do is the neural network parameter update. And this is quite tricky because we've sort of had a well-defined like hypothesis function or a forward function, if you will, of what our y hat was. So in the case of linear regression, it was wx or plus b, I guess, because I mean the plus b can be ignored, I guess. We can focus on the wx. Um, and the y hat for logistic regression was basically the logistic function applied to wx. And then there is a pretty good idea of how we're going to get y hat given a value of x. Now, neural networks aren't like that. They can be of any shape, any size, and be as big as you want. Um, and so that's where this idea of a backpropagation comes in. So it's called backpropagation. And essentially what this means is that you have a neural network which takes in a couple of inputs. Sorry. Um, and then it has a couple of intermediate nodes, and then it has a final node, let's say, or maybe even two final nodes. And so what we have is we have y1 and we have y2. And what we can do is we can compare y1 and y2 to y1, y1 and y2 hat to y1, the real value, and y2, the real value. And so if we take all of this in, we can define some sort of cost function. It could be the binary cross entropy cost function as we talked about before, or there's also categorical cross entropy cost function. There is mean squared error, root mean squared error, or absolute error. A lot of different types of cost functions, but somehow we find out how bad we have a way of computing a differentiable way, mind you, which means that you can take the derivative of this function, a differentiable way of computing what is the error of our model with respect to all of the um, how do we sorry how do we compute the cost, right? And it's not with respect to anything because we're not like differentiating anything yet, right? How do we find this cost, right? Let's say there's a way. And so now you have this cost and you want to for example, there was a W10, let's say, that was used over here in order to um, you multiplied H1 by W10 in order to put that into this node, right? And how would you get the update for that value, DJ DW10? How would you get that? Or more importantly, for this one right here, like W3, right? How would you get it for this one? Or for this one? Or for this one, right? Well, what you would do is use the chain rule. So if we can find, suppose that we want to find DJ, well, let's say this one right here is like W20, right? Um, let's say we want to find DJ DW20. What we could do is we could use the chain rule and we could split this into the two problems. DJ dy hat. And let's say there's only one output. So there's only a y, right? For the simplicity's sake. So DJ dy hat, and then multiply by that by dy hat dw20. So what I'm saying is that in order to find j, we need y hat. But in order to find y hat, we need W20, right? And to find DJ DW20, we could just use the chain rule and split it up into a problem of this thing is easier to find because I know how to find find the derivative of the cost function with respect to any of its inputs. And I know how to find the derivative of y hat with respect to any of the weights that were used to compute it, right? And now we can find out, based on this, well, based on whatever our rules are of computing y hat and computing j, we can find out these two and then just multiply them together to find out this. And this would help us update the parameter W20, right? And so concretely, if y hat was equal to W20 times x1 plus W21 times x2, right? Where actually, let's call this H2, H3, H4, and H5, right? So this would be taking in okay. So this would be taking in H4. And let's say W21 is used over here. So times H5. So y hat would be computed as H4 times W20 plus H5 times W21. That's all I've written over here. H4 times W20, H5 times W21. And we want to find the derivative of y with respect to W20, right? I don't know why I picked the number 20, but here you have dy dw20 is just, if you're taking it with respect to W20 specifically, everything else over here would be considered as a constant. So you would just have H4. That is your answer, right? So this would be H4. And then this would be based on whatever your cost function is. And we've derived that before. So you would just, whatever this is times whatever this is, you would multiply them together and then get the update for dW20 or like W20. And let's say for W10, well, we want to get dj dW10. How is that even possible, right? Because W10 is all the way here and J is computed all the way here, right after you have the output. Well, again, we can split this into multiple subproblems. We know that that in order to produce J, we need to know y hat. In order to produce y hat, we need to know, let's say, we need to know W20. And in order to produce W20, we know that we need W10. So we can split this into multiple subproblems, right? And eventually, or actually not W20, this would be H4, right? DH4. So we would find this would be H4. So we would find this is based on your cost function. And then dy hat dH4, well, we could come back up over here and then just differentiate this with respect to H4. And that would actually give us dy hat dH4 is actually W20, right? So then this would be this would be W20. And then this thing would be, let's say H4 was equal to sigmoid of W10 times, so H4 is equal to sigmoid of W10 times H1 plus W11 times H2 plus W12 times H13, right? So W10 times H1 plus W11 times H2, hopefully I'm doing this correct, yeah, plus W12 times H3. And then that is how we get H4, right? But now we want to find dH4 dW10. So get the derivative of this with respect to this. So that would just be the derivative of sigmoid would just be sigmoid of whatever times 1 minus sigmoid of whatever, right? And then that would be multiplied by, because of the chain rule, would be multiplied by h1, right? And if you think about it, this whole thing is actually just the value of h4. So we can reduce this down to the h4, because h4 is defined as the sigmoid of everything, right? And then times 1 minus h4. This is also h4. And then this is just h1. And this would give you this. So now we would get something like this from the cost function. Just take the derivative of, like, let's say, actually, maybe I can do this one too, right? Let's say j is equal to y minus y hat and then squared, right? Now you want to find dj dy hat. All you have to do is do 2 times y minus y hat, and then do times -1, I think. Yeah. And then this would be like negative, actually, this could just be 2 times y hat minus y, right? And so this would be this first term, right? And so sorry for getting really messy with it, but all I'm trying to say is that if we want to compute dj dw10, right, the derivative of this final cost function with respect to something that's way earlier on, we just use the chain rule many times. We split that up into a problem of finding dj dy hat dh4 dh4 dw10. We compute all of those separately and then multiply those together and combine that together. So that's all backpropagation is, just finding derivatives of things based on the rules that were created, that were used to create those things. And in packages like TensorFlow, or so I'll say, like, TensorFlow, and PyTorch. So these are Python packages, Python being the programming language. In Python, TensorFlow and PyTorch will have tools to get the derivatives automatically. So they have tools to do backpropagation automatically. And they use this thing called a computation graph, where essentially they split everything down into its most fundamental pieces. That let's say my y hat is equal to w1 x1 plus w2 x2 plus b. So what they'll have is they'll have like really elaborate diagrams of like x1 and then w1, and then we took these together, we multiplied them, and then you had x2, w2, you took these together and you multiplied them, and then you have also a b. So you also have a b, which is at the end, and then you took these three, you put them together, and then there's an add function here. And then you get y hat. And so now, based on this computation graph, if you want to take the derivative of anything with respect to anything that came before it, right? That's how usually these things work, that you take the derivative of a function with respect to the things that were used to create the function. In order to do that, all I need to do is backtrack my steps. So what was used to create, so I want to find with respect to W1, what was used to create y hat. It is all of these things, which is the sum of all of these things. And then what was used to create, let's say, this thing, it's the product between this and this. And then it basically has logic based on the multiplication function, based on the addition function, based on the sigmoid function, the softmax function, ReLU function, and all of the other functions that have their own derivative with respect to its inputs. It has all of that stored, and so it can split a large computation into many, many smaller chunks, and then it performs this based on this computation graph. And so this is kind of called like a computation graph. And that's essentially how gradient well, that's how the gradient is found, the gradient being the dj, dw, that kind of thing, right? And then you would just update it based on your your sorry, you would update it like this, right? Based on your learning rate and whatever your old value was. So that takes care of backpropagation. And so I'll see you in the next video.